2, Optimal Transportation Geometry Dynamics of the Fields Academy of the University of Toronto. I'll be interested to hear feedback from everybody after it goes. So how was it? And let me know. Please speak up if you have questions. And are you able to monitor the chat or not?
I will, like, 5-10 minutes.
All right. So Joaquin is updating his computer, but he says 5 or 10 minutes he'll be able to monitor the chat as well, which I won't be able to do. I don't think. Let me see. Well, we now have a decent number of people logged in at least. Let me see if I can get the chat up here. Yeah, okay. All right. So let's see, we talked about topology, what, at least for a compact subset of Rn, what topology on the space of measures do we get out of the P Wasserstein distances, and we discovered that the answer was completely independent of P. Now, actually, that's not entirely true, because the P equals infinity case leads to a different topology, and that so for a subset of Rn, the probability if I look at the probability measures on M plus, and I put the P Wasserstein distance strictly less than infinity, PP that causes narrow, wide, weak star, because it's compact set, they're all the same. And P equals infinity leads to a finite topology. So, for example, if I think about the curve, it goes from 0, 1 to 1 minus t delta x plus t delta y, x different from y, and then plus. This curve is a continuous curve for dp. Well, I guess maybe we didn't talk about P equals infinity very much at all, but depends continuously on T for P less than infinity, but is not for P equals infinity. So there's different ways to define one. The simplest way is to say the infinity is going to be the limit as P goes to infinity. But just like LP is a little bit of a different flavor from L infinity, DT has a different flavor from infinity. And I should also mention, when n equals 1, there are nice formulas because we know what the optimal mappings look like when n are 1. Plus U minus, well, of course, this is integral of x minus y to the p gamma of x y here. Probably so. Let's see. Let me right there. Let's see how far over I'm getting on the blackboard. Great. I'm glad that Joaquin's logged in now. I don't know, I can't, okay, great, thanks, Ken. Joaquin, so how far over can I go?
That's the last thing. Yeah, like the two letters, the
Or off, or, okay. And we know that when, so let's see, when n equals 1, basically, gosh, okay, yeah. When n equals 1, the support of gamma p bigger than 1, say it's bigger than 1, support of gamma p is going to be a non-decreasing subset of R2. And actually, there's only one measure that has the correct marginals whose support is not decreasing in R2. And I mean, you could think of that as writing experiment if you like. And one way to write gamma p is to define what are sometimes called the cumulative distribution functions f plus and minus of x, which would be the integral from, well, okay. I'd like to write that it's the integral from minus infinity up to x, du plus minus. And the only problem is that if u plus or minus has Dirac measures in it, then this is a little bit ambiguous. So let me say it's maybe a better definition is u plus minus of the set minus infinity up to x. And then I can make a choice about whether I want it to be open or closed. So these are both non-decreasing maps from the real line into the unit interval. And so they have inverse maps, except I count only many points. So I guess gamma p is actually f, well, let's see. So the optimal map from the optimal map G pushing forward u plus to u minus is going to be something like f u plus inverse composed with f u minus. Right. So this is going to take the real line, the interval. This is going to take the unit interval to the real line. This is going to, I'm pretty sure I have it right. There's some little caveat here, which is that I'm making this more complicated than it needs to be. So I think gamma p. Let me make it less complicated. I think gamma p is f mu plus inverse f mu minus inverse push forward the Lebesgue measure on the interval.
That doesn't appear in the screen.
Sorry, what?
The Lebesgue output measure doesn't appear in the screen.
Oh yeah, sorry. How's that? Did I get it or not yet? Still.
No, but I think people get info.
Okay. I'll write it down here. So this is Lebesgue measure on the unit interval. This guy's defined except possibly at count of many points, but the count of many points defined a set of measure 0. Same thing over here. So this combination of two maps takes this thing on the unit interval into the real plane. And it's going to give you first marginal mean plus and second marginal mean minus. And so that leads to sort of a nice formula for the LP distance in one dimension, which is, so gamma p is this push forward, and I can also write this as the interval from 0 to 1 of f mu plus inverse of, I don't know what to call it, s minus f minus inverse of s to the power. Can't see it here. Let me write it simply. dx. Can you see that?
Yes, yes, yeah.
Okay, perfect. So I'll try to draw the line down.
Sorry, I was responding something.
That's fine. And so there's a nice picture that goes with this. So the picture is that if I have the real line, and I have my measure u plus down here, and I look at this cumulative distribution function f of u plus, wherever the mass of u plus is, these are Dirac masses, it's going to have jumps. And it'll be non-decreasing for less than 1. And similarly for mu minus, wherever the mass of u minus is, and what this formula over here is telling me is that if I want to calculate the peak power of the P Bossenstein distance between u plus and u minus, I need to turn this picture on its side. So I look at the unit interval, and I would have this measure. Maybe looks like that, and another fellow that maybe looks like this. And then you look at the difference between those two things, those two graphs. Yeah, that's fine. So I have these two graphs, f u plus inverse and f u minus inverse. I look at the difference between them, and I would calculate if p was 1, I'd calculate the area between them. And if p is larger than 1, I'd take the p power of the difference. Now, of course, this picture only works in one dimension. But sorry, p power, I guess. And so then it makes it easy to work out what this example is. And also the case, this is also true for the case p equals infinity as a limit. It's the ln, you take the p root on both sides, and then you take the L limit, it goes to infinity. So you have an L infinity right over here. Right. The infinity mu plus mu minus is f mu plus inverse minus f mu minus inverse L infinity 0, 1. And then what you find is if you well, if I looked at this guy for 2 different times, so 1 minus t delta x plus t delta y, 1 minus x delta x plus else delta y. You find that this is, it doesn't go to 0, it has to go to t. It increases to, let's say this is going to be equal to the distance between x minus y for every s not equal to t. And so the idea is, if I have a point mass here and a point mass there, what the LP distance is measuring is how far I have to move the mass of this guy to get it to that guy. What's the farthest distance I have to move? And even, or if I have, let's say, a unit mass here and 1 minus epsilon unit mass, with epsilon mass over here, the distance I have to move is still the distance between x and y. Even though I have to move only a little bit of mass, it's a positive amount, epsilon. And the LP distance measures what's the maximum difference between these 2 things, and the maximum difference between these 2 things is x minus y. So this gives this much finer topology, and that's actually useful in applications sometimes. When I was a PhD student, I was studying a model for rotating stars. And so the question posed to me by my advisor, I always leave it. He said, well, you know, if you have, what is a star? It's a certain amount of gas, maybe made up of compressible fluid. And every little, at least in the Newtonian model, every little bit of gas over here is attracted to a little bit of gas over there by Newtonian gravity, which wants to make the whole gas collapse to a point. And on the other hand, what it means to be a gas is that if you squeeze it, it pushes back on you. So it obeys maybe some equation of state that tells you the pressure is a function of density. And you can integrate PdV to get the total amount of internal energy stored in the gas compressed to a certain amount. And then you can ask, how do the gravitational effects balance the pressure effects to find a steady state of the gas? And so if you fix the total quantity of gas, and maybe you assume there's no, like, let's say the total, we call it momentum is 0, so the center of mass stays fixed. And then you try to minimize the sum of the gravitational potential energy plus the internal energy. It made some assumptions about the form of the pressure then. So if the pressure is strong enough to prevent gravitational collapse and not so strong that it pushes to overwhelm gravity and push all the gas to infinity, then there maybe will be a unique ground state, a unique energy minimizing state, and it will be spherically symmetric with the densest stuff at the center. And so you use rearrangement inequalities to show this, and I guess the Reese rearrangement inequality. The densest stuff will be at the center, and it will be decreasing density as we move out. And again, depending on what pressure you assume, it probably the density gas will go to 0 at a finite distance, so that the star will not extend to infinity. It will have a fixed boundary. But the question my advisor asked was, well, what if the star is moving? So what if there's some total angular momentum? If it's spinning around its fixed center of mass, then can you perform this energy minimization? And it looked fairly bleak. In fact, he said, well, the problem is, of course, that one way to satisfy the angular momentum constraint is to take a teaspoonful of mass and put it into an orbit far away, where it can satisfy, it can move slowly, but have lots of angular momentum and very little kinetic energy. So it can it can satisfy the angular momentum constraint, having as little kinetic energy as we like. And so you can actually, by doing that, you can actually approach the non-rotating minimum energy by letting the mass be smaller and smaller and further away. But that doesn't sound so physical. And so after sort of grappling with this, so that actually this problem is how I got into optimal mass transportation in the first place. But after grappling with this problem for a while, kind of the understanding that I came to was that probably, okay, there's no global energy minimizing state, but you can still have local minima. And one example of the kind of local minima you can, if the angular momentum is small enough, you might have a single connected local minimum, but you can also prescribe a mass ratio and have a binary star. And if either the if the mass ratio is unequal enough, depending on the size of the angular momentum, then you can construct the binary stars in arbitrary mass ratios where you have maybe a big component and a small component orbiting each other to satisfy the angular momentum constraint. And it would be energetically favorable if you could sort of evaporate mass from the small component and transfer it to the large component. But at least in this d infinity topology, that's a discontinuous thing. And so you can't have local energy minimizers in the d topology for any p, any finite p, but you can still have local energy minimizers in the d infinity sense. And I think they're cool. So I think binary stars have this flavor. And you people, I mean, physicists that study binary systems, you can see things like if they're too close together, there'll be like a little mass bridge where mass is actually drained off the smaller one and onto the larger one, and it's just until they get too far apart to do that, and then they're sort of barely in equilibrium. It perturb it a little bit because they have a little bit more mass. The lighter one to the larger one. So this is a feature. The fact I would say that the fact that this P equals infinity leads to a finite topology is a feature, not a bug. But on the other hand, it's not a vector space topology, because in a vector space topology, whenever you evaporate mass from one component and grow it on the other one, this for a vector space topology, this has to be a continuous function. And so, of course, weak convergence is a vector space topology, and so that's for P finite, you get weak convergence, or whatever, narrow convergence. But for P infinity, you don't get a vector space topology on the space of measures. Okay, great. And so yeah, so I did this stuff about rotating stars, gosh, when I was a PhD student 25 years ago, almost 30 years ago. And it sort of didn't really take off for a long time, but now more and more people look at it, and it's turned out that this d infinity topology is actually relevant to other problems which have been more actively pursued in applications. So Cameron has worked on this a little bit, particularly where you have these swarming models where you have lots and lots of organisms, and every organism is maybe attracted to every other organism if they're too far apart, repelled if they're too close together, and you want to understand what are the equilibrium that the organisms will find. And certain parameters regimes you could find local minima for the infinity topology, which are not necessarily globally defined, but they're still stable, and you could look for them, finding in simulations and so on. Okay. Well, let's come back to finite p for a while. What we showed. So what did we say? We said this net causes narrow convergence. And if M is compact, then P of M plus is closed at complete. Respect to narrow convergence, and so therefore, back to and it turns out if M plus is Polish, so where we're at. Because the let's see, So the sum of Ti delta Xi the countable events. I claim that I take the union over natural numbers K, set of some Ti delta Xi, where the Ti are non-negative, and let's say rational, and maybe sum to 1. Is a countable event set in the sky. Did you see that? Sorry, where did the K come in? Oh, sorry. I guess I didn't need to do this if I let it myself that into it sums. Okay. Other questions? So this is, you can actually see this as the Krein-Milman theorem if you want. So you can think of the probability measures on M as sitting inside the let's say the Banach space dual compactly supported functions, which is not a Banach space, so it has you have to make functions that vanish at infinity if you want. This is sort of the weak star topology over here, and we know that dp metrizes the weak star topology. And this dual is a locally convex topological vector space. And because these all sit in the unit ball and form a closed subset, at least when M plus is compact, Banach tells us that this is a weak star closed set. We start compact. In this topology, in this dual topology here. And it's also a convex set. And so Krein-Milman says that EM plus is the closed convex element of stream points. Sorry. Wait, that's the line. It's supposed to go past. And so that tells you that it's the closed concept. Then it's good to go back to finite K. So Krein-Milman says that this should be the convex hull of its extreme points, and then closed with respect to the weak star topology. And so my claim is that the delta measures are exactly the extreme points of this convex set. So U plus now it's pretty clear that these delta measures are extreme only because if you decompose a delta measure into a sum of two non-negative measures, they both have to be concentrated at point x. And conversely, if you have a measure that isn't concentrated at a single point x, then it has two distinct points in its support. And so you can take a neighborhood of one of those points in its support and the complement, and write the measure of the restriction to the neighborhood and the restriction to the complement. There'll be some complex combination of those two points. So this, you can see this, the density of the things, the consequence of the prime. And so what we basically see in this example is that the nice structure of M plus being Polish, at least in this example, gets replicated at the level of the space of measures. And the fact that M plus is compact gets replicated in the compactness of this thing with respect to this weak star topology that they're trying to make. The second point, the first point is equally nice if you look at unbounded sets, that it's still true that the space of measures in the DT topology, space of measures with piece moments in the DT topology is still going to be a polar space. It doesn't inherit the compactness properties in quite such a nice way. So now I'm going to talk, so far I've been talking about the topology. Now let me talk a little bit more about the metric structure. So when I wasn't smart, triggered lots of chalk here. Okay, so
Professor,
yep.
why is it sufficient to have the delta size just the countable dense subset of delta, like the measures on the direct measures on only that subset?
Right. Okay. So
Because that's not the whole set of straight points.
right. So
I mean, it's like
so you have to check that so it's the same thing. In the Kroneman theorem, I wouldn't restrict to rational TIs. I don't look at all real TIs. But so you have to check that if you have some TI, let's say TI tilde delta XI tilde, maybe I say delta Y, with YI tilde in M plus and TI real between 0 and 1. That so things like this are certainly dense. That's the kind of sure. And then the question is, can you approximate everything like this by a guy like this with the xi's in the countable dense set and the ti's rational? And we know that you can find xi's because this is a countable dense set. For every yi tilde, you can find an xi as close as you like to it. And for every ti tilde, you can find ti rational as close as you like to it. And so you have to check the dp distances that be arbitrarily small. Right. Thanks for the question. Other questions? So. Right. So so whenever you have a metric space, MD, and you have a continuous curve, sigma, let's say, there's a natural notion of the length of this curve, which you can get by looking at partitions with line and adding up the distances between the endpoints. So this should sum actually. Sum I equals 1 up to k distance sigma y sigma si minus 1. And then you can define a related metric to be the shortest curve connecting x and y. So you look at all continuous curves, fixed endpoints. And that's the minimum length of the curve. And in principle, that defines a new metric, tilde, which is always, I think, bigger than the old metric. Because one partition might results less than the old metric. So in principle, this defines a new metric, d tilde, but I'm mostly, so if d equals d tilde, d is called the length space. And if in addition this infimum is attained, then M tilde, call the geodesic. Well, I'm going to call it a geodesic space. Although I guess in Romos, we should probably call these path metric spaces. And so my claim is that at least if we assume a little bit more, we assume that the M plus is actually not only compact but also convex, then the dp is going to make the space of probability measures into a length space, which is also a geodesic space. So the first one we have a remark. Yeah, maybe I should give you some examples. Yeah, right. Take an interval. And take x minus y to the alpha power, alpha between 0 and 1. Call this the. Yeah, now I run into some trouble with my notation. So let me call this d alpha, I assume super alpha or something. Right. That's good. So you can check that. So the remark is that for every alpha between 0 and 1, the alpha is a distance function. So in other words, it satisfies the triangle inequality. But that's remark 1. Remark 2 is that B alpha tilde equals B1. So this is not a length space unless alpha is equal to 1. And you see, so you see that here's the Euclidean distance, and here's the square root of the Euclidean distance. So you see that, for example, D1 half is bigger. And I think that's the general phenomenon of details is always less than. And so my claim is that so my claim is that as long as the domain is a compact convex subset of Rn, that when you put any of these dp metrics on it, what you get out is a geodesic length space. And moreover, the geodesics here are going to be of interest to us. So, and then one more remark here. So, if x and y are in M, 1 minus tx plus ty is the Euclidean geodesic. And joining them. And 1 minus t, sorry. So the interesting thing is, what is the dp geodesic joining delta x and delta y? And it's not 1 minus t delta x plus t delta y, which we already saw is continuous, but rather it's the Dirac mass sitting at this convex combination. So the picture somehow is that when you want to interpolate between this Dirac measure and that Dirac measure, instead of shrinking one and growing the other, you slide the first one to the second one. And somehow, for a lot of purposes, that's a more natural thing to do. And if that's a more natural thing to do, then the dp metric may be a good metric for your problem. So let me see. So we'd like to understand these geodesics a little bit. So in order to understand them, let me make a remark. A sufficient condition for this continuum to be attained is maybe I don't want to quick erase that yet. So if there exists a curve sigma such that the distance between sigma s and sigma t is a fraction t minus s, or even let's say is of the distance between its endpoints. For all s and t. And And sigma changes the supremum. Yep.
Ask some questions. Yep. So does the length of a curve always exist? Aren't there like a Bible?
Well, okay, look, it's a supremum of things. And so what does a supremum mean? It means it's the least upper bound, right? So the least upper bound could be infinity, but it still exists. I mean, I don't say the length is always fine. But, so. Right, and so you could worry about this d tilde as d tilde really, d tilde could be an infinite value metric. I mean, I say d tilde is still a distance function, but infinite value distance functions are not too bad because you can always replace them by tilde over 1 plus d tilde. So double tildes like this. And that will take a thing which would be a metric except sometimes infinity, and it will convert it into a thing that takes values between 0 and 1. So the infinity value. And without changing, it won't change the quality. And it will still satisfy the triangle quality. So okay, you have to check to satisfy the triangle quality, but basically you didn't exercise like this in the one context like concatenation occurs, so it still satisfies the triangle quality.
Each tilde is always a metric.
Yeah, it's always a distance function, although it might take the infinity somewhere. So d tilde, d double tilde is always a honest metric. But anyhow, as I say, I'm mostly interested in the cases where you need tilde coincide. So I haven't been thinking much about what happens with it. Although this is the canonical example where they don't coincide. So in fact, it's enough that it's enough to get one inequality for free. So I think it's enough that you have this, right? Basically, because of the triangle inequality, i.e. Let's say the length of sigma is bigger than or equal to all these things. So in fact, the principal is bigger. In particular, it's bigger than the sum as I comes from 1 to k of sigma si minus 1 for all partitions. And maybe I better go back to, yeah, right. So that's backwards. So let me just see. We'll come back to that in a minute. So if I have this equality here, then I basically have a telescoping sum. So I would have si minus 1 distance sigma 0, sigma 1. This would come out, and this would be a telescoping sum that boxes to 1. Sorry, and I guess this is tilde length. So because, well, I guess I need a bit more. So this shows the length of sigma. but it's the supremum over things like this. So no matter how I partition it, I always get this number. And so even when I take the supremum, so I have an equality over expressions like this, partitions like that. But each of these is the same number. So if you have a guy that does this, then the length of that curve is equal to the distance. And so it's a geodesic. And then I actually said, well, it should be enough that we have one inequality, and which is an inequality. So the length of a curve is always longer than the distance between its endpoints. And so it should be enough that I have this inequality here. And somehow the opposite inequality comes from the triangle inequality. So geodesics are basically characterized by this property. And we call such sigma d geodesics or d tilde geodesics. D geodesics. So this inequality is basically how you recognize a geodesic. And so then I want to come back to the case where I'm dealing with one of these metrics on one of these spaces, and show that they're actually geodesic spaces, and and understand what the geodesics are. So the proof of this claim relies on the characterizations of geodesics with respect to the P. And so when we try to state this characterization, well, let's do one direction of yes, so this is one. So gamma point measure is optimal. And what we can do this explaining the points x and y. Then I claim is a so the claim is that there's this connection between optimizers in the Kantorovich problem and geodesic curves in the space of measures with respect to these DPs for P bigger than 1, less than infinity. And of course, I want M in this case to be a convex subset of Rn because I want, when I take a convex combination of 2 points in M, that this is again in M.
Then addition is gamma.
Thank you. Other comments? Okay. So this is not too this. So there's two directions here. I mean, actually there's a converse to this theorem as well, but let me not worry about the converse at the moment. But the converse says that every DP geodesic arises from an optimal measure. So I'm not too worried about the converse. What I'm mostly worried about is showing that this is really a geodesic space. So I want to show that this construction does the trick. And if that's true, then this example will be clear because when u plus and u minus are Dirac measures sitting in x and y, what this construction is doing is it's finding the Dirac at the point 1 minus sx plus s1. And so how am I going to prove this? I'm going to prove this by checking if the dp satisfies this inequality along this curve. That's the step sequence. So that maybe I should have said, and obviously US equals 0 plus plus. And we want to estimate and of course it's this will be less than x minus y to the p gamma for every gamma or less than ut. And so we want to construct from gamma p a measure gamma having marginals be less than ut. But we already know that pi x pushes forward gamma p to a marginal guy having marginal us, and pi t will push forward gamma p to a fellow having marginal us. So if I choose pi s comma pi t pushes forward gamma p with one of the competitors. And so let me choose that to my competitor, So I could call this gamma PST. And since it's defined as a push forward, then I would have pi s xy minus pi t. So this is, maybe I should call this z and w, where z is pi s of xy and w is pi t of xy. And then if I remember what pi s and pi t were, I'm going to see that this is like 1 minus sx plus sy minus 1 minus tx plus ty. And so this is going to be something like s minus t, t minus s, x minus y. And now a very nice thing happens, which is the t minus s comes out to the p power. And what's left over is basically this thing, which is equal to the distance between the endpoints. And so by taking the p through of this thing, I've shown that it satisfies exactly the property that I wanted in order to have a geodesic, FEP geodesic. And so a nice example of this occurs when it's two, recall two, we have this nice characterization. Two plus absolute two is respect to vague. So the US in this definition, IS push forward, identity cross to U push forward plus, but when you have two push forwards, it's like a composition. So we have 1 minus S times the identity map plus S to U plus and so it turns out that there's nice characterization in this case. Equals 2. Well, it would work for any, but let's do plus absolute continuous for something vague and plus minus is down in our X. Then that implies that US on each geodesic and if you want to write the density of this, so rho S, which is HN, it's going to be related to the density of the initial line plus by, so let's call this mapping. Let's say yes, X. That's U of X. Density rho S of GS of X is exactly the density at time 0 at x divided by the Mondor-Pure determinant. You would expect the Jacobian determinant now. So this is du is approximately differentiable almost everywhere. So yes of x 1 minus s to the identity plus s, the approximate derivative of u almost everywhere. And that's what you're doing here. And so you can really characterize these intermediate things in terms of the initial density of this kind of Mondor-Pure expression of Jacobian. So let me tell you a little bit about what goes into this theorem. Well, really what's mostly going into this is that what's mostly going into this is that u convex so what's I never know whose theorem this is, Luzin or somebody. If you have an L1 function, it agrees, or even a measurable function, it agrees with a continuous function except on a set of arbitrarily small measure. Right, perfect. So so this theorem gets reproduced at the level of first and second derivatives. So for example, if you have a Lipschitz function, then it agrees with a C1 function except on a set of arbitrarily small measure. If you have a convex function, it agrees with the C2 function, except on a set of arbitrarily small measure. And so convex implies for every epsilon within 0, there exists u epsilon, which is C2, such that the Lebesgue measure of the set u different from u epsilon is less than epsilon. And so by choosing a countable, you can take these sets to be decreasing as epsilon goes to 0. You can choose a countable sequence of epsilon goes to 0, since these are smaller and smaller sets. And so this is basically what's called so i.e. u is countably C2. Find a countable sequence of C2 functions which agree with you on sets, except on sets which are going to 0 as the countable sequence goes to infinity. And so what does that mean? That means GS is countable Lipschitz. And so if G was an actual Lipschitz function, then this kind of formula would come out of like the area or coordinate formula, in fact, both, because we're doing a case where you're mapping a set of given dimensions, or set of the same dimension. And because it's countable Lipschitz, you can get a countable iteration of the co-area or area formula. So let me quote, for example, Sant'Ambrogio. There's a version of this in Sant'Ambrogio. There's also a version of this in Milani. You can find this in Sant'Ambrogio. 115 or Milani. This is probably the second book of Milani. So let's say the deep Milani. Sant'Ambrogio. If rho is L1 positive, C is omega 2R T. All right, yeah. It's countable Lifshitz. With non-vanishing Jacobian. Zero, then the image measure is absolutely continuous with respect to hemisphere measure, and here's the formula. It says this image measure at y is the sum over pre-images of y, the initial measure at x divided by this Jacobian determinant. And he says that this simplifies, or I'm going to say that this simplifies to the inverse of y divided. So there'll be only one thing in this sum. Sorry, I switched. I keep switching between his notation and my notation. And so to get from the sum over pre-images to the single pre-image, all we really want to understand, which is basically what I wrote over here, all we really want to understand is this graph GS is injective, 1-to-1. And then basically what I bring down is this theorem here. And so how do I see it's injective? So injectivity of GS. So I want to look at GS of x minus GS of y. I want to know that if that has to be non-zero if x is different from y. And so let me look at the inner product of this with x minus y. So this is 1 minus s x minus y plus grad u, there's a grad u somewhere, plus s grad u of x minus grad u of y. And so this is 1 minus s x minus y squared plus s grad u of x minus grad u of y x minus y. But because u is convex, this is non-negative. So this is bigger than 1 minus s minus y squared. And by Cauchy-Schwarz, the first guy here is less than GSX minus GSY in more context minus y. And since x is different from y, that's all the x minus y. And so I've actually gotten a stronger conclusion from this little argument. So I've gotten that GS of x minus GS of y is bigger than 1 minus s x minus y, which says, so not only is this non-zero when s is less than 1, and x is different from 1, it's actually telling me that that the map G is not contracting things by more than a factor 1 over s. But not only is its inverse defined, its inverse is not expanding things by a factor more than the inverse of 1 minus s. So in other words, I've actually shown that GS inverse exists on its range and it has a Lipschitz constant. And those 1 over 1 minus x. So I showed much better than that it's injective. I showed it's actually invertible. It has Lipschitz inverse. Of course, the Lipschitz constant blows up as s goes to 1. This thing, you know, imagine you're mapping everything to a graph massive point. At time 1, it's not invertible anymore. Everything's been mapped at the same point. So G for S less than 1, GS inverse is actually a pretty nice map. And then this kind of here, which again I call it's a consequence. Gives me this nice representation of so many. Since I don't have a lot of time left, maybe a nice thing to do is I'll just say what the area co-area formula are. It's not everyone's in them probably, and I think Evans and Uriah P is a nice reference for the area and co-area formula. Well, and then maybe I can also say where are we going with this. So having this nice representation of what the densities look like along these interpolating geodesics are going to allow us to do things like compute the LP norm along a geodesic, along a D2 geodesic, or compute the Boltzmann entropy along the D2 geodesic. And we can see things like that the LP norms and the Boltzmann entropy are going to be convex functions with S along these geodesics. And that's actually telling us something about Euclidean space. It's telling us things like isoparametric information in Euclidean space. And that you know, ultimately what we're going to do is we're going to throw away Euclidean space and live in abstract measure spaces which are geodesics, and assume the convexity of things like the LP norm or Boltzmann's entropy and deduce isoparametric information. But anyhow, let me just write down the area and co-area from this. That'll be useful for seeing this in Euclidean and also the Riemannian case. But I'm gonna sort of, because I don't want to give a course in Riemannian geometry, I'm going to skip the Riemannian case, and those of you who know it, and look it out yourselves if you're interested. Or you can look at Riemannian's book, which is heavy. The big book of Riemannian is heavy on Riemannian. So it's a variety. So if you have, so this is, I'm going to let F be a Lipschitz map from one Euclidean space to another Euclidean space with dimension M. And basically, this is all about, you know, how do I integrate the Jacobian of this Lipschitz function against the weight measure? And I'm integrating either against the smooth test function or against the characteristic function of set A. And now the difference between the area and the co-area formulas is the domain higher dimension than the range or lower dimension than the range. And in the case where n is equal to m, you can use the co-area formula and the area formula interchangeably, which is the case that we've been mostly talking about. So in the case where you're mapping from a lower dimensional space into a higher dimensional space, the answer to this integral is given by the area formula. And it says you can integrate over this subset of lower dimensional space. It's like integrating over the higher dimensional image space. But then you have to count the number of points in the higher dimensional space whose pre-image intersect under F intersects A. And like this too much. So what I definitely going to target. So this is what I have in my notes. And I guess most points, pretty much most points not going to intersect A, so this will be sort of a rare event. And it tells me I'm integrating against the n-dimensional measure. And whereas if I'm in the case where I'm mapping from higher dimension to low dimensions, then right, okay. So in this case, I'm mapping a low dimensional space into high dimensional space. It's like you have a surface, you're mapping into 3 dimensions. The surface is going to be a thin set in 3 dimensions. And so it's going to have 0 3-dimensional volume. And so to get anything at all here, I need to integrate against something like area. So I hope to get it. And that's what I'm doing in this case. And if I'm mapping from a higher dimensional space into a lower dimensional space, then I'm probably, typically I'll cover the lower dimensional space, and every point in the lower dimensional space is going to have a whole submanifold with 3 images in the higher dimensional space. If this was, think of this as being C1 instead of Lipschitz. Then each point in the lower dimensional space is going to come from a n minus m dimensional submanifold in the higher dimensional space. And so I'm going to be integrating the h m minus n measure, right, n minus m measure of the intersection of that submanifold with A. And then I integrate it over the full lower dimensional space. So this is what the area of the area formula are. But they're basically telling you, they're like changes of variables in when you see in second year multivariable calculus, and you see when I want to do a change of variables through a function f, think of the case n equals m. Then I'm integrating some arbitrary test function, it's just in this case, in characteristic function A against Jacobian is equivalent to doing something on the other side of it, other than change of variables. And so here it's what happens if you do this. If your test function is characteristic function A, you basically do something like intersection of that. But again, in the case where f is a diffeomorphism, it's all simpler, and m is equal to m, then there'll typically be 1 point in this intersection. That's basically the change of variables formula. So, so a corollary is familiar. And more general questions. Okay. Any questions? All right, thanks a lot. I guess that's a good place to stop.